After seeing an overview of different quantum dots and their functionality, we focus on the key ingredients for quantum information: readout, initialization, single and multi-qubit control. The spin of an electron may be read out in different ways. When the spin energy levels of an electron in a quantum dot are aligned with a nearby reservoir, such that the spin-up energy is above the reservoir and the spin-down energy is below the reservoir, readout may be achieved with what is called Eltzerman readout. This energy-dependent tunneling results in a change of charge only when the electron is spin up. This change in charge can be measured using a nearby charge sensor. After this sequence, the energy levels of the quantum dots are lowered. The quantum dot is occupied with an electron. The spin of that electron will be spin down, since only an electron with spin down could initially tunnel back to the quantum dot. Thus, using this method, we simultaneously have a method to read out and initialize a quantum dot. Another method for spin readout is based on the Pauli exclusion principle. The Pauli exclusion principle states that no two electrons can reside in the same state. Thus, an electron in the state spin down cannot tunnel to a quantum dot that is already occupied with an electron in the state spin down, unless it has enough energy to go to the next excited state, which is higher, for example, by the orbital energy. Note that we have seen before that in silicon there is a valley degeneracy. Thus, in silicon, Pauli spin blockade may be limited by the valley splitting energy, rather than the orbital energy. Nonetheless, by carefully aligning the energy levels in a double quantum dot, electrons can tunnel from one to the other quantum dot only for certain spin configurations. This method of readout is called Pauli spin blockade, and it's a very effective way for quantum information, as the quantum dots that are used to create the qubits are also exploited for the readout. That is, no external reservoirs are needed anymore. In addition, the readout signal itself is no longer a blip in time, but a change in signal that lasts until the blockade is lifted. For example, due to a relaxation process where the spin of an electron flips, or intentionally by voltage pulse, because you want to continue the algorithm. Now that we understand how to read out an individual electron spin, we can turn to qubit control. We first focus on single qubit gates and consider an electron in a magnetic field. The spin states of the electron are split by the Zeeman energy. We can learn from the time-dependent Schrödinger equation that the time dependence of the spin-up and spin-down wave functions differ by a phase that evolves with a frequency corresponding to the Zeeman energy. This frequency is called the Larmor frequency. If we consider an electron in silicon, where the G-factor is close to 2, and a magnetic field of around 1 Tesla, the frequency is around 28 GHz. Indeed, the spin of an electron in a magnetic field is processing really fast, and for coherent qubit control, we need to keep track of this phase. Mathematically, it is convenient to work in what's called rotating frame. That is, we define a frame that rotates with the Larmor frequency, and consequently, we can describe a spin state in a static magnetic field using the time-independent Schrödinger equation. If we want to execute a qubit operation, that is, we want to coherently control the spin state, we will need a term that couples the spin-up and spin-down state in the rotating frame. These terms correspond to the off-diagonal terms of the Hamiltonian, as an off-diagonal term will lead to time evolution, where an electron initially in the state spin-down will rotate to the state spin-up. These rotations are called Rabi rotations. But we need to remember, however, that while these terms may be constant terms in a rotating frame, in the original frame it corresponds to an off-diagonal term that oscillates with the Larmor frequency. Thus, to realize Rabi rotations, we need to apply an AC magnetic field with a frequency close to the Larmor frequency, determined by the Zeeman energy, and it should be applied in a direction orthogonal to the static magnetic field. Such an AC magnetic field results in Rabi rotations, and by controlling the phase of this field, we can control the axis over which we make rotations. Controlling the time and phase over the AC magnetic field, therefore, provide universal control for single qubits. That is, we can access any point on the Bloch sphere by controlling the time and the phase of an AC magnetic field on resonance with the spin qubit. And this is the key to single qubit control. We will now examine how these AC magnetic fields are made in practice. We can realize such an AC magnetic field by applying an AC current through a microwave strip line that is close to the spin qubit. An AC current, like the sine wave here, will result in an AC magnetic field. If we write this in an exponential form, we can observe a clockwise and a counterclockwise rotation. If our static magnetic field is sufficiently large, only one of the two rotations is relevant. By tuning one rotation to be on resonance with the qubit frequency, the other rotation will be off by twice that frequency. Neglecting this term is called the rotating wave approximation, and it is usually a good approximation as long as the Rabi frequency is much smaller than the resonance frequency. While a current through a strip line will generate an AC magnetic field that can be used to drive single qubit operations, it is not very efficient, and Rabi frequencies are typically of the order of a few megahertz. The energy needed to drive is not very local, but fortunately there are other methods for qubit operation. If a small magnet is placed near the spin qubit, a magnetic field gradient will be present. And by applying an AC electric voltage, the quantum dot will move in that gradient. Electric fields can be made local, and this can be a rather efficient method of driving with qubit operation frequencies on the order of a few tenths of megahertz. Still, there is even a more efficient method for qubit driving. Electrons in semiconductors can experience a spin-orbit coupling, and this can be very strong, in particular for holes. Similarly to the nanomagnet, the spin-orbit coupling results in an off-diagonal term in a Hamiltonian. Thus, by applying an AC electric field on resonance with the qubit energy, we can achieve Rabi driving thanks to the coupling of the spin to the orbital motion. Using this method, speeds beyond 100 MHz and even up to a gigahertz are routinely achieved. Qubit operation can be so fast that it's even hard to keep track of it with classical systems. While this may sound impractical, it also means that qubit driving requires very little power. Power dissipation is a key concern in classical computing, and it is expected to be least of similar importance in quantum computing, and low power driving is therefore crucial. In addition, this method of operation does not require extra building blocks, such as strip lines or magnets, but just the same gates that we already used to make the qubits in the first place. That is, we are really morphing the classical transistor into the physical qubit. For single qubit rotations, we just discussed that off-diagonal terms lead to Rabi rotations. 2-qubit gates can be realized in a similar manner, but by considering the Hamiltonian of 2 qubits rather than 1. In order to execute a 2-qubit gate, we need to create off-diagonal terms in a Hamiltonian that couples the spin-down state of one electron to the spin-up state of another electron. This interaction is called the exchange interaction. In quantum dots, the direct exchange interaction is rather small. Intuitively, this can be understood by observing that the direct interaction is connected to the probability that an electron tunnels from one quantum dot to the other quantum dot. And simultaneously, the other electron tunnels in the opposite direction. Whereas in real atoms, this coupling can be very strong, in quantum dots, the tunnel coupling is usually much smaller. Therefore, the direct exchange interaction can often be neglected. Instead, electrons residing in different quantum dots can couple to each other via the O2 charge configuration, the situation where two electrons reside in one quantum dot. Compared to real atoms, the orbital energy is typically much smaller, and the consequent interaction is therefore much larger. Furthermore, using the electric gates, it is possible to tune the energy such that the O2 charge state is rather close to the 1-1 charge configuration. Due to the Pauli exclusion principle, the lowest O2 charge state is usually the singlet state. And as a result, only the singlet 1-1 charge state can couple to the O2 charge state. And this results in an effective exchange interaction. If we now focus on the Hamiltonian and, for example, initialize our system in the state spin up and spin down, time evolution will result in an evolution to the state spin down, spin up. And this operation is called the swap operation. In quantum dot systems, there can also be a difference in Zeeman energy between the two quantum dots. Due to this difference, the evolution will no longer be a perfect swap. The rotation is along a tilted axis. And in fact, when the Zeeman energy difference is large, much larger than the exchange interaction, the evolution will lead to an operation called the Z-phase. In this regime, one qubit, which we will call the target qubit, will acquire a phase over time that is dependent on the state of the other qubit. The single qubit operation, together with one of these two qubit gates, provides a universal quantum gate, and in principle is sufficient for fault-tolerant universal quantum computing. Instead of this time evolution, it is also possible to actively drive a two-qubit gate. We can observe that the exchange interaction results in a change in resonance frequency. This change is dependent on the state of the other qubit. Thus, the target qubit has a resonance frequency which is dependent on the state of the control qubit. And therefore, we can execute a two-qubit gate like we realized Rabi rotations for a single qubit gate. Applying an AC magnetic field on resonance with this new resonance frequency results in a controlled rotation. This two-qubit gate, where rotation is made dependent on the state of the other qubit, is called the CROT, the controlled rotation. The controlled rotation is very similar to the two-qubit Z0 gate, with the difference only being a single qubit Z-phase. Extending the two-qubit gates to multi-qubit gates is possible by realizing that we can tune the exchange interaction. Starting from an isolated qubit, we have a single resonance frequency. By exchange coupling this qubit to another qubit, we observe that the resonance frequency splits into two lines. By driving at one of these frequencies, a CROT operation can be created as just discussed. Now, if we couple 3 quantum dots, we observe 4 possible resonance frequencies. Driving one of these frequencies will result in a two-fold controlled rotation, a 3-qubit gate. And that is, we change the state of one qubit only if the other 2 qubits meet a certain condition, for example, all pointing down. Such an operation is in the class of the Toffoli gate, or specifically, it is called an I-Toffoli. For comparison, a Toffoli gate requires at least 5 2-qubit gates when decomposed in single and 2-qubit gates. The ability to do multi-qubit gates is thus highly efficient. But we can also couple 4 quantum dots to each other. In that scenario, there are 8 resonance frequencies. Now, driving one of these resonance frequencies will result in a 3-fold conditional rotation, a 4-qubit gate. And that is, we change the state of one qubit only if the other 3 qubits meet a certain condition, for example, all pointing down. While a 2-qubit gate together with single-qubit operations is a universal gate set, it is evident that the opportunity to realize such multi-qubit gates will lead to more efficient implementations of quantum algorithms. The key question is thus whether the reduced overhead by applying multi-qubit gates compares favorably to the added complexity and possibly faster decoherence, since by opening more channels, there are also more ways to experience noise.